Okay, so very good morning and welcome to the fourth day of the Gyan program. Actually, if you look at the schedule, we were expected to have Professor Karmalkar start with the Himalayan ophiolites. Unfortunately, he is unable to join us today. He will join us tomorrow. So, I will continue the next lecture that was supposed to happen in sequence with his. So, I will be talking about a little bit about UHP metamorphic terrains in the Himalayas, and we know that in the Indian Himalayas we have one very well established UHP terrain. So, first of all, this work is of course ongoing with the JET, and that is why I put the logo there, but yeah, it is something that we started way back in 2008. When we went to field for the first time and looked at these eclogites which were ultra high pressure, and then subsequently work has evolved. So, I will be giving primarily a petrological perspective and not a geodynamic model, okay, because that is not something what we do, we work on the petrology. So, I will give you that. We all know that we have seen this cartoon from Oliver's slides, and we know that the continental crust subducts to mantle depths, and that record is primarily preserved in rocks which sometimes undergo high pressure and very rarely ultra high pressure metamorphism. Okay. So, when you have the continental crust that subducts, you primarily have what we call as there has to be something that is actually dragging this continental crust down, and that is typically your oceanic crust or something denser. Okay. So, in the Himalayas and in many ultra high pressure, in many orogenic belts, you see that the denser crust, okay, which is primarily oceanic in composition, or it could be gabbroic or basaltic, typically gabbroic. That subducts to great depths and then it comes back sometimes, it bounces back sometimes. Okay. So, the geodynamic record of subduction and subsequent exhumation can be studied now by looking at orogenic belts which possess ultra high pressure to ultra high pressure metamorphic rocks, and these rocks are typically represented by your blue schist facies rocks and your eclogites. Okay. And they are able to tell us what is the history of this subducting slab. Okay. Not everywhere in orogenic processes, not all orogenic belts have ultra high pressure or high pressure, mostly high pressure, but not all the time ultra high pressure rocks preserved, and that is why when we find them, it is very important to understand both prograde or subduction processes as well as exhumation processes. Okay. How do you understand whether a rock has undergone ultra high pressure metamorphism? It is primarily by the presence of index minerals like coesite, and which is the high pressure polymorph of silica, and when you have that present either in its pure form or as a relict, or when it is as a pseudomorph. Sometimes most of the times you do not find pure coesite, you find the pseudomorph, or you find the alpha quads. Okay. So, when you find that, we know that the crust has reached UHP levels, okay, ultra high pressure levels, and that can be summarized or looked at in this graph or in this PTD diagram, which primarily tells you that when the crust is subducting, it has to reach this depth somewhere about 100 kilometers at least for it to undergo ultra high pressure metamorphism, and anything below that is typically high pressure metamorphism. Okay. So, metamorphism of crustal rocks, both the continent part and the oceanic part, when they subduct to depths greater than 100 kilometers and they are able to crystallize coesite as the index mineral, then you know that we have reached UHP levels. Okay. So, this is typically what we use to understand the subduction and the exhumation history of our rocks. Okay. If you look at the global occurrences, of course, I think it was in 1953 that coesite was first found in natural rocks. Okay, so it was experimentally tried before that, and of course subsequently, but Coes was the first one who identified coesite. I think that was in the Western Alps in Dora Maira. I'm not extremely sure where he found the first. Chopin, okay, Chopin was, but yeah, so Coes identified that silica has a high pressure polymorph, which is coesite, and Chopin was the first guy who identified it in the Dora Maira. So the Dora Maira then got established as an ultra high pressure metamorphic complex, and subsequently you have several more. So you have the Western Gneiss region in Norway, which is here. You also have the Dabi Sulu in China, which is somewhere here, this is here, and of course you have some in the Alps. So you have also in the French central, in the Massif Central. You also have some in the Greenland province. Okay, and China has now several localities in China have now people have identified the coesite and now have started to move from a high pressure to an ultra high pressure complex. Okay, India or the Indian subcontinent is unique because we have the subduction there, we have the suture zone, but it was very recently, it was only in 2001 that the coesite was identified in two locations, one in Kaghan in Pakistan, and then subsequently pretty much the same year or the following year in Somorari. So it's these two locations which sit very close to each other and very close to the collisional boundary or the belt, you know, the, what is that called, the, yeah, so it's close to this point here. Syntax, yes, where you actually find both the localities. Okay, so of course after this a lot of research has actually happened on ultra high pressure metamorphism. People have started to look at that more seriously and not just say that yes, coesite is found in meteorites or in extraterrestrial material, but we also find it on the earth and primarily in continental settings. Okay, so some very classic or common structural and lithological characteristics were observed between these different terrains. Okay, and primarily all of them were lying between major continent-continent collisional belts. So we didn't have, so yeah, it was when two continents collided, there was a possibility of finding UHP rocks. And these are of course photographs from the Somorari, because I don't have photographs from other locations. But it's, if you look at literature, especially the paper by Liu et al. In 2001, it shows that, or he says that most of these terrains which are now UHP, recognized UHP terrains, they all have several similarities, and they primarily have pods or lenses of mafic material which have undergone, which have basically been subducted to depths and now do show UHP signatures. So they occur as pods or slabs within typically what we call as gneisses, okay, quartzo-feldspathic gneissic units, and these pods, they preserve the UHP signatures. Okay, of course most of these, because we are in the continent-continent collisional belts, they have continental affinity. So the chemistry, the geochemistry also shows that we are in a continental setting. But then the question comes as to why do we have this pod which is mafic, and where is the mafic material coming from? So of course we are looking at an older protolith which has then got subducted with the continental crust and then exhumed back, and the exhumation is primarily because of the buoyancy of the lighter material, the felsic material, which is bringing it all back up. Okay, so these actually lie at structurally higher levels in most units. So we look at Somorari as an example and understand that. The exhumed crust now lies as a thin sub-horizontal slab in the upper continental crust, and it is bounded by normal faults. Okay, so if you look at the structural aspects of many of these terrains, you have similarities. So they are bounded by normal faults at the top and reverse faults at the bottom, and probably that aids to in the exhumation process. I haven't really worked on structural aspects of these, especially of Somorari, but it's there in literature. Okay. What we also find is that we do not have any island arc, volcanic or plutonic equivalents associated with these terrains. So there is no subsequent magmatism that was happening, it was just an exhumation process. And yes, we do find late stage granitic plutons which are associated very close to them, to these terrains, and in Somorari we have the Ladakh batholith which is very close. So if you look at Somorari and you look at all the parameters that have been laid out, it fits the bill of at least from field observation, it definitely fits the bill of being very, very similar to other UHP terrains which you find world over. Of course, we need to confirm all of this by petrography, geochemistry and other aids. Okay, so we did that. We sampled these rocks way back in 2008 and we've been subsequently sampling them whenever we go to field, and every time we go we look at something different and we are trying to kind of unravel the story a little bit better. Okay, so if you look at the Himalayan belt, you have, like I said, Kaghan, which is the, where is Kaghan? This is Kaghan, and I've marked it in the wrong color, I'm sorry. So, no, sorry, the blue ones are UHP, so you have Kaghan which is UHP and Somorari, and everything else should actually be in red. So yes, we do have places where you do get high pressure rocks, so primarily blue schist facies and eclogite facies sometimes, but the coesite has not been identified, so we do not put them under UHP category. Okay. Coming to Somorari, we have looked at this map earlier. Okay. So if you see, Somorari is a very small 100 kilometer by 50 kilometer square kilometers body. It's a crystalline, it's a crystalline complex which sits right below the suture zone. So this purple band is the suture zone, and you have the ophylites, the Nidar ophylites which are sitting on top. Okay, what is very interesting about Somorari is that it's now established that it was primarily the leading edge of the Indian continental plate which got subducted and then got exhumed back. Of course, the models, there are several models which have been proposed by Dissegoy, by Julia and other people like Stefan Gouliet, but I'm not going to go into the details of that here. If you look at this geological map, of course these are sampling locations. Most of the eclogites that you find in the Somorari, they are all retrograded except for two we found which were pure eclogites, and they preserved all their minerals intact and they didn't actually show retrograde features. But everything else is actually a retrograde, it's retrograded to amphibulite facies. So we are typically looking at processes during exhumation more than what we see during prograde. So that is typically what happens with metamorphism, because it kind of obliterates at times all the prograde signatures and you are left with retrograde signatures. Okay. If you look at the map, it's a dome shaped or an oval shaped structure. This is primarily, the yellow is the quartzofelspathic gneisses. So it's extensive and they are highly deformed at places and grading to, in fact, at some places to myelonites also. But since that was never really the focus of our attention, and maybe now we'll switch and look at the crustal rocks also, or the felsic rocks also, we kind of never really worked on those. Okay, but some people, very few people have worked on those in literature. If you look in the literature, you will find information about the quartzofelspathic gneisses also. But the eclogites have been intensely worked now because they preserve the coesite, they tell us different things about subduction, histories, etc. of the, at least of the Indian tectonic, of the Indian plate. So yes, if you look at these field photographs similar to the earlier field photographs, let me go back, in fact that one is a better slide, a better photographs because they are recent ones. Yeah, they occur as pods. Okay, so this is the primary eclogite which is pure, it does not show retrograde signatures. Okay, and all of these lenses which are actually at higher structure, at a higher level. So they are quite, this is like maybe 100 meter, more than 100 meters height, okay, and we are already at 5,400 meters elevation above sea level, so it's quite high. So all of these pods or these lenses, in fact, these slightly black lenses, there are several of them. There are more than, I think, 100 there, okay. They are all retrograded, okay, and they show retrograde features in terms of their minerals, and we'll look at that a little later. So they actually have a very sharp contact with the host rock, and it's not a gradational contact. Even this one here, there are some faults on both sides, but yeah, this is how the eclogites look in the gneisses. Okay, so field wise, other than the quartzo-feldspathic gneisses, which probably have more structural elements preserved in them, the eclogites just look like boudins or lenses, or that's all. They don't really show any signatures. Of course, the core of these lenses are more coarse grained. As you go towards the edges, they are more fine grained, and those kind of features are definitely observed. Okay, coming to the established PT path, this has already been published in literature actually. So there are several people before me. I have not put the references here, unfortunately, I am sorry for that. But these PT paths were kind of worked on by several workers before me. What I tried to do was, I tried to put this into the perspective of petrology, okay. And I'll show you that first. So if you look at this PT path, we know that the eclogite started, or the protolith which got metamorphosed to form eclogite started at, of course, crustal levels, and then got subducted to depths up to 120 kilometers, and then it came back up, okay. But how do we understand that? We understand that, at least we have done it through the petrography or the petrology, and you look at these rocks, they are beautiful coarse grained rocks which have large garnets, okay, and they have other minerals like omphacite, which is the soda rich pyroxene. You have phengite, which is the high silica mica, amphiboles, which are typically sodic in composition. So you have baryosite, and some places, not here of course, but you have, yeah, typically baryosite, and then quartz and coesite, which has been identified. So all the previous workers who kind of worked on these rocks, I think Sachan was the first one. Sachan Mukherjee from Wade Institute was the first one to identify coesite, and he tested it with the help of the Raman. Subsequently, no other worker has actually found the coesite in the slides. Okay, I think it's a chance preservation. Fortunately, we've been able to do that. We got them in our slides, and we got several of them, several grains. So we got 8 grains, which actually are coesites. So of course, I'll show you that later. We have a lot of secondary mineralization or secondary minerals like the zoisite, the epidote group mineral. We have the feldspar. Of course, we have the pyroxite, we have the chlorite, and then we realize that these are actually retrograde products. They are not the primary peak UHP products. Okay, so typically garnet, omphacite, okay, phengite, amphibole, and at places quartz and coesite. Okay, this is how they look. They are beautiful euhedral idioblastic grains with cores full of inclusions, rims which are relatively free of inclusions, and of course at places completely devoid of any inclusions. Okay, these are the grains which are the coesites. You can see they are characterized by the typical radial cracks, and those are nothing but expansion cracks because of during exhumation. So they are expansion cracks, volume, the volume increases, so it cracks the host mineral. Okay, these are of course garnets which have got retrograded to chlorite along cracks, and they are more rounded, and they are not as idioblastic as the UHP signatures. Okay. Based on all these minerals which occur within the garnet cores, we were actually quite confused as to why we are getting amphibole, sometimes even mica and other things within the cores, and what do they represent. So we realized that it's at this point we have already reached UHP stage, and there is no way to understand what the protolith was, or where did these rocks start from, what was the starting point. And later on, when we actually analyze them with the chemistry, we realize that all these inclusions which are present even in the backscattered images, you can see it very clearly. The light is too much, I'm sorry, but yeah, all these inclusions typically represent the pre-UHP phase. So they represent the protolith, parts of the protolith which are actually preserved. So all these minerals like the amphibole, the sodic amphibole, the epidote, the clinozoisite, all of them which are present in this are typically represent the pre-UHP stage. And another thing that we caught was the zoning. The garnets are intensely zoned. So at lower pressures or lower temperatures, they are most calcium rich, and as subduction increases, they become more Mg rich. So that was so this association was established, and yes, confirmed with previous reports that all these minerals which are present within the garnets are actually a pre-UHP assemblage, and then you move as subduction or metamorphism increases, prograde metamorphism increases, you get signatures of garnets which are more Mg rich in the rims, you get the presence of omphacite, and you get the presence of coesite. Okay? So yes, the second phase or the second association would typically be a more calcium rich garnet in the core and a magnesium rich garnet in the rim, with the presence of omphacite and coesite. Okay, and of course rutile and fengite, they are all accessories. Like I said, we were able to identify the coesite within our samples. We found several grains, so these are 6 or 5, no, this is the 6th one, yeah. So 6 grains of coesite, which we then of course confirmed petrographically, because there are again in literature different ways to actually confirm whether you're actually looking at a coesite, and of course we confirmed through Raman studies. Okay. If you look at the coesites, they are typically always elongated, small grains, and they have what we call as an isotropic halo around them. If you look at them, they are typically surrounded by these very intense radial cracks. Okay, that's a characteristic feature. Even when the coesite completely transforms to alpha quartz, you should get radial cracks, and that is a, what do you say, diagnostic indicator of whether coesite was present or not. The radial cracks help you to understand that. What do you also see in this image is very, very clear. You see a nice rim and you see a core, and this rim is nothing but the coesite changing to alpha quartz during exhumation. Okay, so they will typically have different textures under the microscope. Okay, so this rim is called as the palisade quartz texture, and it is very, very well preserved in these samples. Okay, not every place on the earth actually has this. So we were lucky enough to actually get this, and we've been able to do more detailed Raman mapping to understand whether this actually works. Okay, so all these grains in fact have both the phases in varying proportions. So coesite, quartz, and they are, so what we could capture was typically how the transformation goes. So you, at places like here, you get complete transformation. So the amount of coesite which is left in the grain is very less. This is of course in natural samples. We could only understand how this works by looking at experimental data. Okay, so experimentally, at what depth, especially at what temperature and what pressure complete transformation takes place has been done by workers like Perilat. He was the one who actually gave us the detailed transformation of coesite to quartz, and we use that to understand this information better. Okay, so I'll come to that. I'll come to what temperatures, you know, these transformations work with, or what happens a little later. Atoll garnets, another very fascinating observation that we found in these samples. So you have whole porphyroblastic garnets, okay, which are full of inclusions, and you also have garnets which have a central part which are completely occupied by another mineral. So here it's phengite, it's the mica which is occupying the central portion, or I would say so this is the central core, and then you have a mantle region which is now occupied by phengite. And this was peculiar because not a lot of information at that time, at least when I started the work, I realized that I don't know why this is happening, whether it's a UHP stage formation or it's post UHP, no idea. But when you looked at backscattered, they also showed zoning. So they are zoned, they have Mn rich rims, and you also have some part of the core which is calcium rich. So they are following compositionally the same signatures as the whole garnets, but there's something else that's happening here which was kind of difficult to understand at that point, but yes, we've been able to figure that out now. So if you look at the atoll garnets, they are typically a nice euhedral shaped garnet with a central well preserved core, and you have between the core and the rim you have an association of different minerals. Okay, this is also actually associated with symplectites of calcium rich amphiboles, plagioclase after garnet. So we realize that by looking at the texture of the other minerals, we are probably looking at a post UHP phase, and these are not UHP. So this is something related to exhumation. Okay. So here the calcium, so the garnet is again Mg rich at the rims. I have not put that map, yeah, it's here. The Mg rich at the rims, and you also get calcium rich amphiboles, plagioclases, biotites, etc. Like I said, all these garnets are zoned, and the zoning ranges from a calcium rich core to a magnesium rich rim. Okay, so calcium Mn rich core with a Mg rich rim. And of course we then used coexisting mineral phases like phengite and garnet, phengite and CPX, garnet and CPX to then calculate temperatures. You know, at what temperatures were these minerals equilibrating and remaining stable. So we did that for both the whole garnets. The core, like I said, was full of inclusions, so we used the phengite and the CPX in the core of the garnet to come up with temperatures, and we used different thermometers. The one that really fit the best was the garnet phengite, because they seem to be in perfect equilibrium. So we get a temperature of 635 degrees. Of course, I have not worked out the pressure here because you need other minerals which are stable to calculate pressure. So pressure was calculated based on garnet, CPX and phengite at 2.8 GPa. The rims of course showed higher temperatures, which was of course because you're subducting, the crust is subducting. So you're getting higher temperatures at the rims, which is nearly 800 degrees Celsius, and you're getting there was no pressure that was calculated here, so we didn't use a barometer here. When you looked at the atoll garnets, we realized that the pressure is in fact, the temperature is in fact dropping. So out of these two traverses, I don't remember which traverse we use now for these calculations, but the range of the temperature is now 614 to 675, so definitely lower than UHP. So the rim of the garnet represents the UHP temperature of nearly 800 degrees. Okay, and the atoll garnet represents a lower temperature, or it's at a lower temperature at a lower pressure. So then that gave us an idea that maybe this is, like I said, post UHP. Yes, we get different other minerals which are primarily post UHP. You get garnets which are intensely fractured and now filled up with chlorite. You also get biotite, which is a low temperature mineral now. You get hornblende. Okay, you get a lot of symplectites of plagioclase and CPX symplectites of plagioclase after CPX, and of course you get the calcium rich amphibole, which was not present earlier, and also this is in fact the sodic amphibole which is present. So if you look at the amount of retrogression that the rock has undergone, these are some possible reactions that could have taken place to give rise to the amphibole and the plagioclase. So the omphacite would typically break down, sorry, the omphacite in the presence of quartz and water would break down to form the amphibole. So that's how the transformation, we believe that happened. If you look at comparing the data that we generated on the whole garnets and the atoll garnets and compared that with the experimental work by Perilat, we realized that there was a very good match. Okay? Based on these images, the Raman mapping images, what we did was we used a software, an open source software, an image processing software to calculate in this area how much coesite could ideally be present and how much quartz could be present. And with those numbers, we then looked at what experimental data says. And it says here, I can't read very well from this, but it says that the quartz to coesite transformation, which is the complete transformation of 100%, happens at a temperature close to 800. Okay? So this is 800 and the pressure which is given is 2.8. So of course the pressure doesn't match very well, but the temperature definitely matches. Okay, so that was one. But see, nowhere in our slides or in our samples we get complete transformation. There's always a little coesite left. So you have to take these values with a little pinch of salt. But it matched well with what we found for our garnets. Sorry, I'm going back. So it matched well. So when you say 800 as peak transformation, because quartz would transfer to coesite at 800 and we are getting a value of say 768. So that kind of matched well. And again the retrograde transformation of coesite to quartz happened at 2.3 pressure GPa and the temperature was somewhere around 700. So that also matched with our values of 675 and 2.3 GPa. So that gave us a fair understanding that maybe we are on the right track, especially with these temperatures. But of course, there was no way to confirm it other than this. We had to use this data to make sense of what we were seeing in the coesite and the quartz transformation. So yeah, near complete transformation of alpha quartz to coesite probably happens between temperatures of 700 to 800 degrees at 2.8 pressures, GPa pressures, and coesite undergoes partial transformation to alpha quartz during exhumation between 600 to 700 degrees Celsius, and that is confirmed by both textural studies and Raman mapping. And of course, we have confirmed it also through experimental work now. Okay? Yes, if you look at this PT path which I showed in the beginning, we try to fit all the petrological work or all the petrological data that we generated in this PT path and these are our garnets. Okay? So you actually start with nucleation during at the onset of subduction. Somewhere at 1.1 GPa, 500 degrees Celsius, and approximately at a time of say 57 million years. So that's when the Indian plate just started to subduct beneath the Eurasian plate. Okay? Followed by garnets which are formed. Okay? These are typically garnets with euhedral boundaries, idioblastic, and they have inclusions of amphibole, clinozoisite, etc., and that represents a part of the protolith which has got subducted, and now you are at 30 kilometers depth. So you are still within the blue schist facies, you haven't really crossed into at least high pressure, ultra high pressure. Followed by the formation of the coesite with the omphacite. This is typically at higher temperatures, 760 or nearly 800 degrees Celsius. 2.6 GPa somewhere at 53 million years. This is typically what you would find for this association of rock of minerals in the eclogite now, in the pure eclogite. And now we have actually crossed the coesite quartz boundary. So we typically have the formation of coesite. Okay? Of course, these garnets or these rocks have now started to exhume back, but we still don't see that in terms of the petrology. You still get higher temperatures of say 780 degrees. This has actually not been recorded in any of my thin sections. I haven't got this number, but Preeti Singh from Delhi, University of Delhi, she has worked on these and she has got this association. So I have still put it there. So 2.8, so I should put the reference there. In fact, I should update this. But what we realize is that most of the minerals which have OH in their structural setup, they start to break down, okay, because of the onset of exhumation, and you have a lot of fluid inclusions. This is my thin section, so you have a lot of fluid inclusions and especially phengite, which probably start to break down and give rise to the formation of fluids, and then you start having what we know as fluid infiltration within the garnets to then go on to form atolls. Okay, so this is primarily at a lower temperature on the way back, okay, as these rocks are getting exhumed. So at 768, nearly around 50 million years, I've put a question mark here because this has not been worked on. I mean, we don't have this actual age, but it's pretty much between 53 and 47, okay. So typically you start getting the formation of atolls because the fluid starts to infiltrate and it along these cracks in the garnet, and it modifies the interior of the garnet and it starts to replace them with lower temperature minerals, okay. Again, yes, so the atoll, this temperature has been calculated 734 to 614 at 2.3 GPa and 47 million years is typically where most of the atoll formation kind of was complete, and you're able to now see beautiful atolls in the form of these pictures, okay. You also get a lot of symplectites, okay, which is again a retrograde feature, and formation of chlorite, okay, biotite, etc. And of course, these symplectite formations, which is represented here in the form of D, they are of course at a lower temperature of 400 degrees Celsius, nearly 1 GPa, and when the crust is quite shallow now at 29 million years. So this is a sort of petrological perspective on what happened with these eclogites. We also have a geochemical perspective which I haven't shown here, but a lot of movement of all your large iron lithophile elements, because they are fluid mobile, so they actually have kind of been elevated. We've done those mass balance equations and also worked out that yes, these eclogites definitely have undergone some metasomatism, okay, on their way back. I haven't shown that here because I just wanted to give you an ultra high pressure story, and I think I've stopped very early. But yes, this is how the Somorari lake looks like, and this is a part of my field area, the Puga Nices. But yeah, I'm open to questions, so we can have a lot of questions. So if you have anything you want to ask or you want to say. Yes, yes.
So about the cracks around the
yeah.
site. So you mentioned of the hypothesis that it's during the exudation that there is a
volume increase.
Yeah. Could it be that it has to do with the coesite itself, phase change?
Yes, because coesite is denser, so it's more compact, and quartz is not as compact, so it expands. And usually the garnet also shows the cracks, and even the zircon, if it's present in zircon, because for coesite to be preserved, you need a competent host mineral. And the only two host minerals that have been found to be very competent to host the coesite is the garnet or the zircon. And typically it's the garnets in continental rocks, especially in metamorphic rocks like this, but the zircons also are known to host the coesites. And they are what we call as there's something called as a pressure vessel effect, because they are the host is also putting the pressure on the coesite to remain intact. So it's
actually feeds the debate about what is measured in terms of pressure. Is it the differential stress, or is it really the weight of the rock column?
I think it's both.
It might be both.
It's both.
So there might be a way to do some mechanical investigation modeling around the quartzite and the garnet, looking at their differential strength,
Right.
density.
Yeah, I'm sure there must be a way to do that, but someone has to attempt this. I think that can be done more experimentally, not really on natural samples.
And this picture,
Yeah.
so yeah, I think that's very, very compelling. And you can use that. As you were presenting it, I was thinking, okay, we should use that as a probe for temperature or pressure changes.
Yes.
This transformation using the relative proportions. I would say that if you want to do it very more precisely,
Yeah.
you should do it in 3D. Because you never know where the cut is.
Yes.
If it's on the edge of the rim or it's in the middle.
Absolutely. But the problem is, like I said, these coesites are preserved on one thin section with a cover slip, and my biggest.
That's very good. No, that's very good. And
Yeah.
do what you can with what you have.
Yeah.
Maybe one thing that we can do now is to look at where these 6 samples come from. Are they from the same rock or are they from different structural levels?
Same rock.
Same rock.
They're from the same rock, from the same sample, and unfortunately, yeah, it's from the core, the rim of that body. So it's not from the core. Yeah, it's from the rim. So.
You could do this type of, if you're lucky enough, you can do a transect across that eclogite body and go from core to rim, and then also look, so that would be one way to look at the relationship between these reactions and the textural position within the
Okay. But you know, very frankly, we have not really sampled all the lenses. It's just impossible because some of them are very at great heights. But if you attempt it,
looking at samples from different structural levels.
we should do that. Someone has to volunteer to climb and break the samples. Yeah.
Other than eclogite, in which rock samples did you encounter cohesion? Not in much greater amount, but at least just the encounter.
So I think in literature, it's only the eclogite that actually hosts the coesite. You could also get the coesite, yeah, so it's either coesite or diamonds, microdiamonds, but they are all in the eclogite. There is no other rock which will have the coesite. Yeah. Yes, Deepak.
How does phengite influence the pressure temperature part?
So phengite is primarily a high silica mica. So when you have, so biotite is at a lower level, and as the crust subducts, the mica will change to phengite. So the silica content is, I think, about 3.5 SI cations. So that helps to, in fact, tell us about, so the equilibrium with, that's why we use that as a thermometer with the garnet, because it's high silica. Yes, somebody had.
You said something about symplectite. What is that?
So symplectites are nothing but two mineral phases which kind of coexist together. I don't know where the picture is, but they are typically a result of breakdown of the original mineral. So the omphacite here, or the pyroxene, is breaking down to form plagioclase, feldspar, and that's through a reaction. So they basically have a symplectic association. So they occur together. You are able to see both the phases, mineral phases.
And in terms of major elements, chemistry, these eclogites, where do they stand in terms of silica content?
So they are typically basaltic. They have a basaltic profile. So like I said, the protoliths are Permian basalts. That's geochemically we have proved that, but I think they definitely represent an older phase. I don't think they're Permian. We still need to figure out. But yeah, they're basalts. So they have silica contents ranging from 48 to 50%, 52, I think.
And you say that, so you mentioned phengite.
Yeah.
As maybe part of it is the primary phase.
Sorry.
The phengite.
Yeah, it is the part. It is the primary phase.
It's a weathered basalt, also something that was
We don't know, we don't have, I can see only the eclogite now, I don't know. And in fact, where these basalts or, you know, they are exposed quite south in the Kashmir side, not in the Ladakh side. So if you say that they are the protoliths, but they've been proved, and we've got signatures, geochemical signatures which say that.
Yeah, what I'm getting at is the fluid story.
The fluid story, yeah.
So you need the idea, the basic idea is that the amphibolite fishes to eclogite fishes transition is related to fluid release.
Yes.
So you identify part of these oily fluids in the OH of the fangites,
Yeah.
primary fangites. But then what is here different from that basic model is that then you got fluid influx back into the eclogite.
Yes. So that's probably because of the,
It's also then sucking back fluids into the eclogite again.
yes.
On the way back.
Yeah, we've been actually able to prove or understand what happens on the way back and not really what happens on the way down very well. But there are some studies which have said that on the way back up you have a lot of fluids which were released. That's been proved experimentally also by a group in Germany. But all these fluid inclusions are probably evidence that in the retrograded eclogites that there was fluids which were present.
You got your amphibole already in the current course, right?
This, yes, could also be a reason for the fluid while going down, yeah.
Also, what are the dating techniques which are used?
So here we didn't use like in situ dating as such, we used thermometers. So we used two minerals which were in perfect equilibrium with each other, and we looked at we probed them, we got their mineral chemistry, and then we worked out the temperatures.
So, ma'am, by any chance, are there any literature showing the fluid inclusion study as such in particular?
So yeah, when we actually got the things, yeah, there are studies. I think only two. There's one by Chatterjee et al., which basically tells you about what kind of fluids were present in the Somorari eclogites. But we didn't attempt that because you need very intense equipment and heating stage and stuff like that, and that was never the primary focus of the work. So we were looking at it more from a petrological perspective. So yes, fluids, because someone has already established them, we didn't kind of go ahead and then recharacterize what fluid inclusions were, what was the composition, whether they had a fluid phase or a solid phase or a gaseous phase. We didn't do that. But maybe if there's someone who's interested, we can retry. Yes, so I think I'll stop because, and if you want, we can take the break now, or we can, has the tea arrived? If it is arrived, then we'll stop. So yeah, thank you for listening, and I hope to work more on these rocks, at least on the eclogites, for something else maybe, and try and, yeah, please.
So the core sites you found in these two locations only?
So yeah, so basically, yeah. So out of the entire sample set, we sampled about 25-30 eclogites, but when we were actually sifting through them, you know, we ended up throwing out most of them because they were amphibolites, okay, and we didn't want to work with the amphibolites, but we realized that we shouldn't have done that actually, because we could have got a better story of the exhumation path. But what we did was, we found two samples which were pure eclogites, okay, and so one of them has the coesite, and one is purely with no coesite, yeah. But
they kind of concentrate only in the northern parts. Down also you showed some.
Very frankly, they are all in this lens. It's in this big lens and this part, and at this structural level where you find them. We couldn't really climb up here because it looks quite accessible, but it's not.
As in geographically, right now it's towards the north, and then as we move towards the east, you
Are you talking about this?
You mark something in blue and red in your location map. The previous.
Okay, this one. Okay, so
the blues actually give you the.
so yeah, this one is actually Somorari.
Okay.
Okay, so I color coded them wrongly, very frankly, and I did this yesterday night, so I apologize for that.
The reds are what again?
The reds are in fact supposed to be the UHP, but they are now just high pressure. Okay, so this is Somorari, and this is Kaghan. So these two locations have the coesite, and everything else is all just high pressure, blue schist.
Suggesting that pipe exists only there then, no?
Because as I told you, right, it's the syntax.
Okay,
Okay, so it's probably preserved there. We don't know. See, a lot of these areas are intensely rugged. Okay, it's first of all, you must understand that we are very, very close to the international border. So there's no access, and nobody really goes there. So Somorari was first, like I said, identified in 2001, and then subsequently there was a DST sponsored field workshop in Tibet, in Ladakh, and there was a team of scientists or a team of geologists that went, and then they reworked on those samples. But a lot of this part is completely not worked on. Nobody has gone there.
What's the syntax?
Namche Barwa, that should be-
Yeah, Namche Barwa is also, I don't know if it's here, but yeah, the Namche Barwa is here, yeah, right. There also you find,
Indus Suture zone that marks the syntax because it marks the collision between the Indian and Eurasian plates. Is it?
the Indus suture marks the contact or the suture.
Yeah.
It's not the syntax. Okay, stop, we'll take a break and come back.